Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Syed Salman Shafqat with you. This is lecture number 22, and hopefully it is second last lecture. In this lecture, study about the production of signals in EPR spectrum and their relative intensities, and further how a signal or electron can couple to equivalent nuclei to produce multiplet in a signal. Then we shall see a triangle that is known as Pascal's triangle. This is very interesting triangle. This triangle will help us to assess or measure the number of signals and their relative intensities in the spectrum of any signal. Then we shall see some examples of various types of molecules. First example is about a transition metal complex, that is vanadilyl acetyl acetonate. Further, we shall see some examples of anions. One of them anion is anion of benzene. And further, we shall see at the end of this lecture EPR spin trapping techniques. This technique is actually used for paramagnetic species, but for those paramagnetic species which have their very less uh, time, stability time. These species are paramagnetic, but they have very short time. How can we say that a species is a short time? I can give you an example regarding this. Sometimes we know that there is always an intermediate in a reaction. When reactants react with each other, they produce an intermediate, and that intermediate is further converted into product. Usually, the intermediate of some reactions have paramagnetic nature but very short lifetime. So that uh, short lifetime having uh, intermediate can be trapped by using different reagents, and we can determine its paramagnetic behavior. Anyhow, in detail I shall discuss this topic at the end of this lecture, and as usual this lecture will end with some assignment questions that are given from this lecture. Relative intensities of signals in an EPR spectrum. Relative intensities are determined by the number of interacting nuclei. If one nucleus interact, all lines have equal intensity. This is typically regarding one atom, means a molecule like uh, hydrogen or carbon. This is a single atom. In this atom, the unpaired electron revolving around the nucleus is 1. That one electron will interact with only one nucleus. And the second case is that there are more than one electron and there is only one nuclei with which they are interacting. So in this case, either there is one electron or two electron or three unpaired electron. If they have interaction with only one nucleus, then the intensity of all the signals in EPR spectrum will have equal intensities. But if multiple nuclei are interacting with the unpaired electrons, means if there is a heteroatomic molecule or heteroatomic transition metal complex or any inorganic or organic species, then the intensity of the signals will be of different, uh, will be definitely different. So this distribution is based upon spin. For spin, half, that is most common spin of a single electron, intensities will follow the binomial distribution. Coupling to single nuclei with n by 2, giving n plus 1 lines each of equal intensity. So the formula will be followed as 2ni plus 1 is equal to 2 into 1, that is 1, into a spin of electron is half, plus 1 will become n plus 1 lines. For example, coupling to a single vanadium nucleus, I will be equal to 7 by 2, which will result in a spectrum of 8 lines of equal intensities. Because the nuclei, there is only one nuclei which is interacting with the electrons. This is relative intensities for I is equal to 1. N, capital N, is representing the number of interacting nuclei, and the numbers given in a ratio are representing the intensities of nuclei. If there is only one nuclei, then the intensity, relative intensity of the signals will be equal to 1. Sorry, if 0, then 1. If there is 1, then there are 3 signals of equal intensities. But if their interaction is with 2, then you can see in this line, there is 2 times 1, 2 times 2, and 1 times 3. So it means the signals will be of 1 to 3 intensities. Two signals will correspond to 1. One signal will correspond to 1, one will correspond to 2, and the third will correspond to 3. And when the number of n is equal to 3, you can see 1 is 2 times, 3 is 2 times, 6 is 2 times, and 7 is 1 time. Similarly, when the number of capital N becomes equal to 4, you can see 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, and 9 signals. But among these 9 signals, some signals will have equal intensities. Like at the terminal, you can see 1, 1, means these two signals will have equal intensity. Similarly, 4 and 4, these two signals will have equal intensity. 10 and 10, they will have equal intensity. 16 and 16 will have equal intensity. And the 19th signal will have the highest intensity. Similarly, when the capital N is equal to 5, you can see the total number of signals are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So among these 11 signals, 5 signals will have intensity in a pair form, like 1 and 1, 5 and 5, 15 and 15, and the signal at 51th will be highest in intensity, and similar relation can be studied for capital N is equal to 6. In the previous slide, we have just talked about the number of signals and their intensities. So in this slide, we can see the intensity, height of the signals. When n is equal to 1, all the 3 signals have equal intensity. But when n is equal to 2, at the terminal there is 1 and 1, and the second is 2 and 2, and the third one in the middle is equal to 3. So it means when there is n is equal to capital 2, there will be total 5 signals, but among 5 signals, there will be 2 pairs of signals having equal intensities. One pair is related to 1 and 1, and the second pair is related to 2 and 2, and the third single pair with highest intensity is related to 3. Further, when n is equal to 3, then there are 7 signals. Among these 7 signals, 6 signals will be in a pair, and the seventh one will be having a highest intensity. The three pairs which are in having equal intensity at the terminals 1 and 1, then the second one is 2 and 2, and the third one is 3 and 3. Similarly, when the capital N becomes equal to 4, there are 9 signals. Among those 9 signals, 4 will be paired, and one with highest intensity will be single. Similarly, when we go to 5, there will be total 11 signals. Among those 11, the 11th has highest intensity, and 10 signals will become paired up, and 5 signals, and there will be 2 signals corresponding to 1 1 2 2 3 3 4 4 equal intensity, and similar relation can be studied in case of n is equal to 6. Simulated EPR spectrum showing coupling of one nuclei means I is equal to 7 by 2, coupling to n equivalent nuclei, each with having spin half, again gives n plus 1 lines. 2 n plus 1 will be equal to 2 into n plus half plus 1 is equal to n plus 1 lines. This is actually how can you judge the number of signals to calculate from a relative. This is a very interesting Pascal's triangle. You need to watch it for 2 or 3 times, and you will be able to understand to calculate the number of signals and the relative intensities. I'm not talking now because I want to give you some to watch this video. Now we shall see some examples. The first example is related to vanadilyl acetyl acetonate. So in this case, uh, vanadilyl acetoacetate, the interaction with the vanadium nuclei, for example, I is equal to 7 by 2. So 2n plus 1 will be equal to 2 into 1, and 7 by 2 plus 1 is equal to 8. So it means the interacting nuclei is equal to 1. So that's why all the lines will be having equal intensity. So you would expect to see 8 lines of equal intensity. So it means this is a EPR spectrum of vanadilyl vanadilyl acetyl acetonate, in which there are 8 lines of equal intensity due to interacting one interacting nucleus. Now we can see the example of an anion, that is anion of benzene. An example of this is shown by EPR spectrum of the radical anion of benzene. You can see that C6H6 has a small dot within the square brackets, which shows that this is an anion in which electron is delocalized over all 6 carbon atoms, and therefore exhibits coupling to 6 equivalent hydrogen atoms. So 2ni plus 1 will be equal to 2 into 6. 6 is equal to interacting nuclei, and there is only one electron. That's why its spin will be equal to half plus 1. So spectrum should be 7 lines with relative intensities having 1, 15, 1, 6, 15, 20, 15, 6, and 1. Basically, these two examples have been presented in this lecture to present to you that the number of lines are dependent on interacting electrons and nuclei, but their relative intensity is purely dependent on number of interacting nuclei. In the previous example, that was about vanadilyl acetyl acetonate, there were 8 signals of equal intensity due to single interacting nuclei. But in this case, as all of you are familiar with the delocalization of electron in an aromatic system, the electron has interaction with 6 nuclei. So the number of signals are 7, but their intensity is different. So in short, we can say that intensity of a signal in EPR spectrum is dependent on interacting nuclei. Similar distributions can be derived for n equivalent nuclei with spin greater than half. It means when there are more than one number of electrons, then the spin will become half plus half, and so on. Coupling to several set of nuclei. In the previous example that was related to benzene, the interacting nuclei was hydrogen, and there were 6 hydrogens. But if the interacting nuclei are more than one, and their type is also more than one, means one interacting nuclei is hydrogen and other interacting nuclei is carbon, and the third interacting nuclei is another atom. So what will happen in this case? So now we are going to talk about such type of cases. That first, coupling to a nearest set of nuclei, largest A value, split each of these lines by the coupling to the next closest nuclei, next largest A value. Continue 2 to 3 bonds away from the location of unpaired electrons. If an electron coupled to several set of nuclei, then the overall pattern is determined by first applying the coupling to nearest nuclei, then splitting of each those nuclei by coupling to the next nearest nuclei, and so on. So it means the intensity or splitting of EPR signal is mainly related to the nearmost nuclei. Another case, that is pyrazine anion. An example of this can be seen in the radical anion of pyrazine, where coupling of two equivalent nuclei, that is 14 nitrogen and I is equal to 1 nuclei, gives a quintet with the relative intensities of 1, 2, 3, 2, 1, which are further splitted into quintet with relative intensities of 1, 4, 6, 1 by coupling of 4 equivalent hydrogens. In the first case, that is vanadilyl acetyl acetonate, the coupling of electrons was with one nuclei, and we seen that the intensities of signal was equal. Then we see a interaction of one electron with the 6 equivalent nuclei, and we studied that there were signals of unequal intensities. But in this case, we have third level of interaction, that is two different nuclei. So initially, first of all, the signal will be splitted due to the effect of nearest nuclei, and then that signal will be splitted into further by interaction with the second nearest or second nuclei. So coupling of four equivalent hydrogens, electrons delocalized over the ring, exhibits coupling to equivalent n is equal n into I plus 1. So 2ni plus 1 will gives us 2 into 2 plus 2 into 2 into I plus 1 is equal to 5. So then couples to 4 equivalent hydrogen. Then the formula will become uh, 2ni plus 1 into 2 into 4 into half plus 1 is equal to 5. So spectrum should be coincident with the intensities 1, 2, 3, 2, 1. Each of these lines should be split into quintet with the intensities of 1, 4, 6, 4, 1. This is a EPR spectrum of pyrazine radical anion. So in this spectrum you can see each signal has been further splitted due to the effect of second nuclei. As NMR spectroscopy does not usually provide useful spectra for paramagnetic compounds, analysis if their EPR spectra can provide additional insight, analysis if the coupling pattern can provide information about the number of nucleotide coupled to the electrons. The magnitude of ion can indicate the extent to which the unpaired electrons are delocalized, and G factor can show whether unpaired electrons are based on transition metal atom or on the adjacent nuclei. Uh, Now we shall talk about the last segment of our lecture, that is EPR spin trapping technology. Many free radicals generated by enzymatic reactions are not stable enough to detect by EPR spectroscopy. Similarly, at the third slide, that was about the contents of this lecture, I told you that not only this technique can be applied to superoxide radicals, hydroxyl radicals, and nitric oxide radicals. Actually, these radicals are produced during enzymatic reactions, and when a biochemist or biotechnologist wants to investigate the kinetics of reactions, he has to be familiar with the lifetime or species produced during the course of reactions. But these species are not stable enough to be detected by EPR spectrometry. So the alternative method or a tool to trap these species is that uh, spin trap, that is a molecule which in its original form does not have any EPR signal, or we can say that is spin trap is EPR inactive, and the species that we want to stable has very short lifetime. That's why unable to be investigated by EPR. So it means that will also will not show any signal in EPR. EPR trap, spin trap, and the analyte, both of these does not have signal. But when we trap our unstable radical into spin trap, then that it will be converted into stable radical. Once it is converted into a stable radical, then it will show a EPR signal. Superoxide trapping examples, that is xanthine or xanthine oxidase. So xanthine is a spin trap, hydroxyl radical is uh, analyte, which is a paramagnetic species but with very short lifetime. But once we treat it with xanthine, so it will become xanthine oxidase, then it will produce a signal. So we can see, just for your information, you don't need to keep in mind or draw the spectra of this species. Spin trapping nitric oxide. Although nitric oxide is a paramagnetic, it is impossible to detect it by EPR directly because being small, it relaxes very fast as in case of oxygen. Thus, special approaches are required to restrict its motion to get reasonable spectrum. For example, dithiocarbamate and its derivatives are used to trap nitric oxide. So here are some dithiocarbamate and its derivative which are presented in this slide. So this is just for your information. You don't need to keep in mind their structural formula or their abbreviations. So to trap NO, N-methyl diglucamine dithiocarbamate is used as spin trap. So after trapping, a adduct is produced, and this adduct can produce a spectrum or signal in EPR spectroscopy. At the end, I have some examples, some questions. So I think so. You have to answer the questions. That is, what is a spin trapping technique, and how can you find relative intensities of a signal in EPR? So in this question, I want to ask you about in three cases. Initially, when electrons are interacting with one nuclei, one type of nuclei, one nuclei. Second phase is electron is interacting with the different nuclei, and the third one is to third level of interaction of electrons. I would like to say thank you so much. Inshallah, we'll see you in next and last lecture. Assalamu alaikum.